So I'm hoping so far we've developed a pretty good understanding as to what a limit is and how it might be different than, say, the value of a function at a point. In this section, we're going to turn our attention to, okay, how do I evaluate these limits? Say if I just had an algebraic equation, maybe I don't have a graph handy. So this is what we're going to be paying attention to here. We're going to talk about different properties of limits and how we can use these to help us evaluate limits. So we're going to start off here with this theorem. It says that if you're working with a linear function f of x, the limit as x approaches a of f of x equals f of a, which is m times a plus b. So essentially this says, hey, if you want to evaluate this limit, you can just take that number, plug it into your function if you're working with a linear function. And we're starting with linear functions here because they're the simplest, they're the easiest to understand, they're what we've dealt with it's what we have the most experience working with. There aren't really any surprises. We know that there aren't going to be any holes, there's no jumps. We have a very good understanding of what linear functions look like. So that's where we're starting right here. So if I wanted to know, if I said, okay, this point right here I'm going to call a, if I wanted to evaluate the limit of my function here, f of x, at this point a, I would say, okay, well, what value are we approaching from the left-hand side? What y value are we approaching from the right-hand side? And in this case, well, we're just approaching this same point, which is actually just the point on the graph. So if I wanted to know, okay, what's this y value, I could find that same y value by just taking that a and plugging into my function f of x. So there's really nothing too weird going on with, left or right-handed limits. Linear functions, kind of what you see is what you get. There aren't going to be any major surprises. So we're going to use this theorem to evaluate a couple of examples here real quick. We've got some linear functions. So in part A here, I want to know the limit as x approaches negative 3 of 5x minus 1. Here, this is a linear function, so if I want to evaluate this limit, I can just take negative 3 and plug that in for x. So 5 times negative 3 minus 1. Here gives me negative 15 minus 1 gives me negative 16. And there's my limit. So hopefully nothing too earth-shattering here. Let's look at B. Here I have the limit as x approaches 5 of 1/2 x plus 4. Again, this is a linear function, so I can evaluate this limit. I can just take 5 and plug that in for x. So 1/2 times 5 plus 4. Here I would have 5 over 2 plus 4, and at this point maybe we think about that as 4 over 1. We get a common denominator, so 5 over 2 plus 8 over 2. This would give me 13 over 2, or 6.5 if you're more decimal oriented. So either one of those I would take. And in this last case right here, I actually have kind of a special case of a linear function. I just have a constant function. Limit as x approaches 0 of 9 here in this case. Well, you could technically say that this is a linear function. It just happens to have a slope of 0, but there's nowhere for me to plug in that x. So no matter what x is approaching, it's always going to be just 9. Nothing's ever going to change that value because there is no x for me to plug that 0 into. So this is a much, much easier way to evaluate some more of these simple limits here rather than having to sketch out the graph of the function. We know, okay, if I want to evaluate a limit, I can just take that number, that x value, and plug it into my linear function. So what we're going to do now is we're going to talk about some other limit properties here, some limit laws, and I'm not going to prove these here, mostly because the proofs are not terribly interesting, but I am going to just talk about them and kind of simplify them, try and describe them in kind of plain English here. So here we have to start off with a couple of assumptions. We've got the limit as x approaches c of f of x and limit as x approaches c of g of x both exist. I don't know what they might be, but we're just going to say that they exist. They're some number. K is some real number here, and n is greater than 0 and is an integer. So n is 1, 2, 3, 4, 5, something along those lines. So the first rule, it's called the sum and difference rule. Basically, it says, hey, you know what? You can take this limit, and for lack of a better word, you can sort of distribute that over addition and subtraction. You can, quote, distribute limits over addition and subtraction here. So this is a really nice property, and we'll actually end up finding out that, hey, these limits actually have a lot of really nice properties. They sort of behave the way you would like them to. Second limit rule here says if you are working with a constant multiple k, so here I have limit as x approaches c of k times f of x. It's easy just to sneak that in here. Essentially, it says, you know what, we can take that and we can kind of factor that out so that it's right here, k times the limit as x approaches c of f of x. So again, kind of for lack of a better word here, we can factor out constant multiples. And this is something that as we get further and further in, you'll start to do without even realizing that you're doing it. But this is a really important underlying property here. The third and the fourth, we've got the product rule and the quotient rule here. Very similar again. Product rule essentially says, you know what, I can take this limit, I can distribute that over multiplication. So again, we can kind of, quote, distribute limits over multiplication. And quotient rule, this one's a little bit harder to see because I changed the notation just so it wouldn't be too small. Essentially, again, this says, you know what, I can take this limit here, I can take this limit, I can apply it to the numerator and the denominator. So I can again, quote, distribute limits over division as long as your denominator, or rather the limit of your denominator, is not equal to 0. And that's just to keep us from dividing by 0. We'll actually talk about that in the next section. Something very particular and very interesting is happening if the limit of the denominator is 0. And so we'll talk more about that in the next section, but just keep that in the back of your mind for right now. 5 and 6 are very similar. We have our power rule and our root rule here. Here, essentially, this says you can carry the limit. So let's get a different color here. The power rule essentially says, you know what, you can carry that limit inside of that power. So I can look at the limit of the inside part first and then evaluate the power afterwards. And then the root essentially says the same thing here. The limit right here, we can again take this into a root. Here, 1 over n, that's actually a different notation for a root, just as kind of a reminder here. If you're working with, say, just like square root of x, this is really x to the 1/2 power. Or if you're working with the cubed root of x, this is really x to the 1/3 power. If we have like the cubed root of x squared, this is x to the 2/3 power. Keep these in mind because these exponent rules are really important. They are going to be really, really important in the next chapter. But essentially, going back to this root rule, it says, you know what, you can take that limit, bring it inside of the radical. This says provided that f of x is greater than 0 for all x near c. I forgot to change that. If n is even. And that last part there is really just saying, you know what, we're only going to worry about square roots of real numbers or fourth roots of real numbers. We just want to make sure that we restrict ourselves to only talking about real numbers. We're not going to worry about imaginary or complex numbers here. So in this next example here, the last example for this particular video, we're going to take a look at a couple of what I call mystery functions here. It says suppose that the limit as x approaches 2 of f of x is equal to 3, limit as x approaches 2 of g of x is equal to negative 6, and limit as x approaches 2 of h of x is equal to 10. We're going to use those limit laws that we just talked about to evaluate some of these limits. So I don't actually know what these limits look like. I don't know what f of x or g of x or h of x look like, but I do know the value of the limit at 2 for each one of those functions. So in part A right here, I would start off, I'm essentially saying, you know what, okay, this looks like a, I was going to say sum and difference, but I guess a difference rule. I'm going to take this limit and I'm sort of going to distribute it over my subtraction here. So I have limit as x approaches 2 of 5 times h of x minus limit as x approaches 2 of 2 times g of x. And then I'll say, okay, well, now I have these constant multiples of 5 and 2, so I'm going to go ahead and use my constant multiple rule to factor those out. Same thing with this 2 over here. So I'll have 5 times limit as x approaches 2 of h of x minus 2 times limit as x approaches 2 of g of x. And at this point here, we can kind of look at this and say, you know what? Limit as x approaches 2 of h of x, we know exactly what that is. We know that that's 10, so I can take that out and just replace it with 10 here. Very similarly over here, I know that, let's grab a different color, let's do this, how about in green, sure. Limit as x approaches 2 of g of x right here, we know what that value is. We said that that's 6. So I can take out that and replace it with 6. Oops, negative 6. Almost forgot my negative sign. And then after that, we're just evaluating this expression. So 5 times 10, that gives me 50. Minus here, what do we got? Negative 12. So I should end up with 62. And this is essentially what we're doing. We're just taking these limit laws and applying them. I would encourage you to do them one step at a time for right now. As you get more comfortable, yes, you will probably be able to jump ahead and do more than one at the same time. When we're very first starting off, though, I would encourage you to take your time and go slowly through these. So let's look at our next one here. We've got limit as x approaches 2 of 4 times g of x over f of x. So let's change up our color here. So again, I'm going to take this limit. I see this division. I can essentially take the limit of the numerator and take the limit of the denominator. So limit as x approaches 2 of 4 times g of x divided by limit as x approaches 2 of f of x. Now, I'm going to hold off on evaluating that denominator. You might look at that denominator and say, hey, right here, this guy, I know that I can simplify that. I'm going to hold off on that because if I look at my numerator right here, this is something that we also know, but we need to deal with that 4 first. And I don't like to start, I like to evaluate all of my limits at once. So I'm just going to hold off on that for right now. That 4 I know I can factor out using my constant multiple rule. So limit as x approaches 2 of g of x divided by limit as x approaches 2 of f of x. And now I can just go ahead and evaluate these two. I've got 4 times limit as x approaches 2 of g of x. We said that was negative 6. Limit as x approaches 2 of f of x. I forget what that is. What did we say? We said that was 3 here. And then after that, we're off to the races. We're just evaluating this expression. So here, what? I've got negative 24 over 3 would give me negative 8 here. One more here, and then we'll wrap up our video. So in this one, I have the limit as x approaches 2 of f of x raised to the 3rd power. So here's where we're going to use that power rule. It says, you know what, for this limit, I can kind of take that and bring that to the inside of my power. So I can say, you know what, maybe it would be easier to say limit as x approaches 2 of f of x, that whole thing raised to the 3rd power. And now I can look at this and say, well, I know what this was. This was given to me in the very beginning of my problem in the instructions. We said that guy was, 3 to the third power. So 3 times 3 times 3, that should give me 27 for this limit. So I would practice a couple of these using these limit laws, and in the next video we're going to see if we can actually take these limit laws and go even further with them to further simplify the process of evaluating more complex functions.